So what we're looking at now is the last little section of this particular unit and looking at our types of bonds. So we get two primary classes at this stage in the game. We'll call them ionic bonds and we'll call them covalent bonds. It is helpful to have a way to differentiate those really quickly. And the easiest way to do that would be to call ionic bonds metals and nonmetals and covalent bonds as any two nonmetals. We aren't looking at metals and metals, and we aren't really differentiating yet, at least our covalent bonds. So when we're talking about our molecules, these kind of segregate out into two different categories. Molecules officially we'll call covalent bonds, and ionic bonds we'll reference as formula units. This is kind of an arbitrary differentiation, a bit of a nuanced system. So if you want to refer to ionic compounds and molecular compounds as molecules, I have no objections to that, and I will probably maintain that. But you may see reference to formula units. It's just referencing the smallest repeating unit of an ionic compound. Why would we need to differentiate these? Well, they have different chemical properties, and because they have different chemical properties, that's why we name them differently. Within the covalent compounds, there are different chemical properties as well. For instance, if we look at the compound H2O or water versus HCl or hydrochloric acid, you probably already know that they have very different chemical properties. And so there are large differences in reactivity within each of these categories, but these are kind of serving as the bulk categorization to help kind of understand those nuances and differences. We'll look a little bit closer at our ionic bonds. I would reference these as kind of the 2-year-olds because these are looking at full-on transfer of electrons. When we're making an ionic bond, the metal is giving up electrons to the non-metal. Because the metal has lost electrons, the metal is equal to a loss of electrons, or mathematically loss of a -1, they become positive. We refer to the positive species as the cation. The anions, or our nonmetals, gain an electron, which mathematically would be plus a -1, which would be a negative, which means our anions become negative. We are responsible for knowing that kind of math behind it, and it does become tricky because we are looking at the transfer of an electron, and that electron is negative. So we have to be a little bit careful with that. They are very regular crystalline structures due to the strong repetitiveness or the repeating pattern within it. We could reference ionic radii, but I do think I'm going to leave that as kind of something for you guys to think about because we're talking about a gain and a loss of an electron. That you should be able to come up with what we would expect to happen for radii with those. But really where this comes in is with our ionic charges. So when we look at ionic compounds, metal and a nonmetal, when they come together, they're going to do this transfer of electrons. And that transfer of electrons means that the metal becomes positive, the nonmetal becomes negative, and we get these charged species. So we get ionic charges. So when you're looking at an ionic compound, and it has to be ionic, you can identify the charge on the metal and the nonmetal respectively, depending on what you're looking at. Those ionic charges hold very regular patterns in a significant portion of the periodic table. So what you're looking at here, which I quickly just modified, is a periodic table with some of the, and keyword there being some, of the metal and nonmetals that you are required to know charges on. And we'll go through and add a couple more that for whatever reason didn't make it to this table. We get zinc +2, we get cadmium, which is a +2, and silver +1. So you're required to know all of those charges, right? And I'm going to add it up here, beryllium +2. It's not a big deal. You'll see why in a second. It is my theory or my proposition that you really only have to memorize those 4. The rest of them, you should learn what their charges are based off of being able to interpret some relatively simple things from the periodic table. And that's coming from this term, isoelectronic, which breaks down into equal electrons. So when we're talking about charge, those elements are picking up a charge or taking or accepting electrons so that they can look like the noble gas, okay, or look like a noble gas. So let's go through and take a look at neon, which has 10 electrons. If we look next to it, we get fluorine. Okay? Fluorine wants to look like a noble gas. Okay? Fluorine comes in with 9 electrons. So it could choose to look like helium with 2, neon with 10, argon with 18, krypton with 36, xenon with 54. We could continue this all the way down. Which of those is the easiest for fluorine to do? If fluorine tries to look like helium, it would have to lose 7 electrons. If it looks like neon, it has to gain 1 electron. If it looks like argon, it has to gain 9. Looks like krypton, gain 25. Okay, and I'm not going to do xenon because that math's outside of my range. So if we look at those as potential options, which would be the easiest to gain or lose? Well, gaining 1 is by far the easiest option. So what does fluorine do? Well, fluorine, given the opportunity, will steal 1 electron. Because that electron, remember, is negatively charged, it gains that electron and it now has 10 electrons. The balance of protons and electrons means that that fluorine would now have a -1 charge. There's the ionic charge. All that's really happening is fluorine's trying to look like a noble gas, and it's easiest to gain 1 electron. If we apply this logic out to other materials, of course I erased it, some stuff here. Let's look at sulfur. Sulfur comes in with 16 electrons. It could look like argon by gaining 2. It could look like neon, which had 10, by losing 6. It could look like krypton by gaining 20. The easiest thing for sulfur to do would be to gain 2 electrons. Remember again, electrons are negatively charged. If I gain 2 negatives, the balance of charge is a -2. So the charge comes from just trying to look like a noble gas. And if we consider how we act in our everyday society, we are trying to look like the nobility. We're trying to show our wealth to the outside world. And you may say that you're not doing that, but the vast majority, on average, people are. Right? This is why we buy fancy cars, why we have expensive phones. The phone that we're using isn't really giving us any more value than anything else. And if you're buying anything from Apple, I'm sorry, it's not usability, it's cost. That's what you're buying. You're buying their logo. Okay, and that's okay. But that's what we're doing. The same thing is happening with elements. They are effectively buying their nobility by trading electrons, and they're trying to do it in the easiest way possible. And that's why we see all of the halogens, fluorine, chlorine, and bromine, will all gain 1 electron to become negatively charged. Oxygen, sulfur, selenium will all become -2. Nitrogen will become -3. We're going to pause and just skip a little bit, and let's jump over to lithium. Okay? Lithium's a little bit different because if we look at lithium, lithium's charge comes out to be +1. And one of your statements might be, well, it's now positive, not negative, so clearly the theory is wrong. Okay? But again, process through this. Lithium comes in with 3 valence electrons. To look like helium, it would need to lose 1 electron. To look like neon, it would need to gain 7. Which is easier to do? It's going to be easier to lose that 1 electron. Remember, we're losing a negatively charged species. That means we come out as positive. There's the charge for lithium. It's trying to look like helium. So the charges are ultimately attempting to look like the noble gases. This is where what I'm referencing here is envision it wrapped on a cylinder. That what we're doing is saying, here's our noble gases. And of course, I spelled that wrong. And this is looping around like a cylinder and coming back. Okay, it is slightly offset a little bit, but it's a cylinder wrapping around. What do I need to do to look like the noble gas? So the noble gases are actually pretty close to a lot of these elements. You'll notice that they aren't close at really all to any of our transition elements. Okay, the transition elements also become a lot trickier to do because the transition elements bring in the d orbitals. And the noble gases don't really have the d orbitals as a primary driver of their electron configurations, which means the transition elements have a different set of rules by which to play. Okay. The other thing I want to address is you'll notice that some of these you don't have to memorize. For instance, carbon. You don't have to memorize carbon. Okay. Well, why not? Well, if we look at carbon, it comes in with 6 electrons. To look like helium, carbon would need to lose 4 electrons, thereby becoming a positive 4. To look like neon, it would need to gain 4 electrons, thereby becoming a negative 4. Carbon's dead set in the middle on either gaining or losing, which means carbon could really be any charge within that. Right? Does it make sense to have you memorize that? Well, if it's going to be anything, why memorize it? We're going to need something else to dictate what that charge is going to be. Right? We need more information. And that's why you aren't told to memorize carbon. However, if you put it in an ionic compound, it typically comes in as a -4. Should you memorize that? No, you shouldn't. Okay? But you may encounter that. When we go through and look at the rest of the periodic table, you will notice that this particular table showed tin and lead as +4. Okay? They're in that carbon family. It kind of makes sense for them to carry that charge. They also carry a bunch of other charges, which means they're not good to memorize as a +4 because you're not always going to see that charge. However, I did add zinc as a +2, cadmium as a +2, and silver as a +1. Right? Those should be memorized. Those, because they're part of that D block, make it a little bit more confusing to kind of use this isoelectronic system to identify. It can be done, but it's probably not worth the effort. And so should just be memorized. I would also kind of argue the same with aluminum. Okay, so those 4 should be committed to memory. The others, you could look at the periodic table and relatively quickly identify them. If you didn't want to be like, oh, well, I remember that pattern, you could also go through on your periodic table, write +1, +2, +2, +1. I would probably circle those so that I knew I was directly referencing those. -3, -2, -1. When we're talking about the elements underneath, for the -1s, we're talking about the non-metals. Right? That's what we're referencing. Those are the charges for the non-metals, not for metalloids or for the metals underneath. Right? Those cause different issues. You'll notice helium, neon, argon, and krypton, and xenon, all don't have a charge associated with them. Again, they're noble gases. Right? Why does everything want to look like the nobility? Well, if you look at their electron configuration for the noble gas, their orbitals or energy levels are filled. Right? And that's the primary reason behind this. The main group electrons are filled all the way out. And That's why everybody wants to look like them, because they're satisfied, okay? They're saturated. So those are our ionic charges. You are required to know those. Those will become much more relevant when we move into nomenclature. And I'm going to say you need to have memorized them then as well. Okay. Here's our Lewis structure rules again. I just want you to be able to see them so that you know that you're supposed to be memorizing these and being able to manipulate them. Right. Our shape summary again. And then we've got Lewis structures for molecules, and these are all listed out. Okay. Because I don't want to force you to go through and look at me solve these examples or watch this out, I'm going to come back to this slide. I just thought of this, sorry, poor organization. But I do want to get to this slide. And in an in-person exam, this is what I would call an exam purge. You would dump this content onto the periodic table that you were given so that you didn't have to hold it in your head. Being able to use notes or not is kind of up in the air. I think you should memorize it anyway, and you should purge it as fast as you can onto a piece of paper. That as fast as you can, maybe before the exam starts, kind of hard to say. We'll hear more about the details on that whenever you take your exam. Okay, but these are trends that you should have memorized so that you could answer questions quickly and efficiently without having to think about where is that content located. And one of the extra things that makes it challenging is note the trends do run in opposite directions, so it can be easy to confuse them. Okay. So I've got 1, 2, 3, 4, 5 different examples that I'm going to go through and work through as far as Lewis structure goes. I will try to talk through this. If for any reason you're like, I got this, I'm done, that's fine. Feel free to stop the video early. I'm not going to arm twist you into it. So we will work our way down through this, starting with this new one with carbon. I am exceptionally, and I'm actually going to make eye contact with this, I am exceptionally anti this question. I think this is ludicrously stupid to ask this, and I don't think it should show up in any textbooks. There's a reason we call it Lewis structures for molecules and not for atoms. By going through and looking at atomic Lewis structures, we overemphasize the placement on atoms, which means the placement for electrons when we move into molecules gets negated, and it's a horrible, horrible plan. That said, sometimes people want to see it, so let's go through and do it. Still follows some of the same basic principles. When we look at carbon, it has 4 valence electrons. There's only 1 atom. We'll go ahead and draw it. Okay. We could again draw our box around our center atom. The one difference when we're looking at atomic theory is that when we place our electrons, we won't pair them. And there we go. We would have a Lewis structure for the atom of carbon. Again, exceptionally anti this. I think it is an awful idea to go through and implement this. But if you wanted to do stuff on your own, you can go through and do it this way. Where this usually moves into is the Lego method for doing Lewis structure. It's a bad method. Do not do it. That said, if you get the answer right, there's not much I can do. So, continuing on, if we move into the next one, we look at ammonium, NH4 plus, nitrogen comes in with 5 valence electrons, hydrogen comes in with, hydrogen comes in with 1, but there's 4 of them. And note that we have a charge this time. So the way that I like to note this is write charge, and because it's a +1, I have to have lost electrons. So that means -1. Okay, and I know that's weird, but again, it's the electrons. The electrons are negatively charged, and that's really what's driving this overall reaction. So when we go through and do the math on this, we're going to end up with 8 valence electrons. Those 8 valence electrons now need to get scattered into our molecule. Hydrogen can't bridge, so we're going to pick nitrogen as our center atom. Again, if I was to box that, hydrogen, 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 I'll place my 8 valence electrons, 2, 4, 6, 8, anywhere I have a pair of electrons between atoms, I'll turn into a bond. Of course, I drew this a bit small, so I couldn't erase that cleanly. Fix that for earlier or next ones. Bond, 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 bond. Check octets. The nitrogen has 8 electrons around it, 2 electrons in each of the bonds. The hydrogens each have 2 electrons because they're in the bonds, so the octets are satisfied. Formal charge shouldn't be fully crossed off here, because what we need to do is provide brackets and say that the overall molecule is a +1 charge. We would just signify that in the upper right-hand corner as such. Okay? I personally get excessively lazy, and that would be good enough for me. I would know that that's not a 7+ because the bracket doesn't make sense like that, and a +7 charge just doesn't make sense either. Okay? And what I now have is a valid Lewis structure for ammonia. If I was then also asked to identify shape, my electron geometry, and my molecular geometry for that matter are going to be the same because there's no difference between bonding and non-bonding here. Check each face. Each face of that square had 4 groups of electrons. So 4 groups meant tetrahedral electron geometry. Because they were all bonding, my molecular geometry comes in as the same thing, and I also get tetrahedral. Okay? Clear it all away, and we can start the next one. The next one is hydroxide. Has a name, which again, you aren't responsible for quite yet. Right after this unit, you'll have that. Oxygen comes in with 6 valence electrons. Hydrogen comes in with 1. If I go through and take a look at my charge, to be a -1, I have to have gained an electron. So I'll be +1 in this case, and I end up with 8 total electrons. There isn't really a clear center atom here. I just have oxygen and hydrogen. I'm going to put my box for my center atom to be on the oxygen instead of hydrogen, but it ultimately doesn't matter if there's no clear center atom. Place my electrons, 2, 4, 6, 8. I have a pair of electrons between atoms. I'll turn that into a line connecting those atoms. Okay. Check octets. The oxygen has 8 electrons around it, 2, 4, 6, 8. The hydrogen has 2. All the electrons are accounted for. Now all I have to do is go through and say formal charge, bracket, negative charge in the upper right-hand corner. Okay, so again, a fairly straightforward Lewis structure to go through and solve. We move to the next one on the list, and these last two become significantly more difficult because we've got a lot of different moving pieces behind this. For those of you that watched the video earlier, you might be like, well, didn't we solve this one already? We actually have not, because what we just solved was sulfur trioxide. This one is sulfite. It's a different compound. Sulfur comes in with 6, oxygen comes in with 6. There's 3 of them, which gets me to 18. The charge in this case is going to be a little bit different too. It's a -2. To become a -2, I had to have gained 2 electrons instead of just 1. So I'm going to add 2 in there. 2 and 18 is 20. I'm getting up to 26. My center atom will be my sulfur. I'm going to go ahead and put that box on that center atom so that I can get that a little bit cleared out. I'm going to go through and show my oxygens, try and give it a little bit of space. I'm going to place electrons now. I got 26 electrons I got to place in here. I'm going to place them starting around the oxygens because oxygen is more electronegative than the sulfur. And I now have 16 electrons. Sorry, I'm getting a bit close up to there at the top. There's 24, and I need 2 more electrons placed in here. I'm going to place it on the empty face of the sulfur. The other faces already have electrons from the oxygens, so I don't want to place there yet. Go through and show my bonds. Okay. Now I would go through and check octets. Oxygen 2, 4, 6, 8. All the oxygens have the same bonding patterns and the same lone pairs, so I don't need to worry about the others. They all had 8. The sulfur, 2, 4, 6, 8. 8 electrons around the sulfur. This has all the octets satisfied. Everything's good to run. All I have to do now is specify the formal charge. can be nice to get rid of all these numbers because that was effectively work. Specify that the formal charge was a -2, and I could circle that upper right-hand corner, and I'm now done. If you remember from the video, this structure had all sorts of resonance stuff, or the SO3 had resonance. 2 electrons makes a really big difference in the overall molecular reactivity and structure. Okay, so it's important to make sure you account for those electrons accurately. Then we have our last one, the nitrite ion. Again, nomenclature, you don't need to know that yet. Right? I'm just including it so you get used to hearing it. Nitrogen comes in with 5 electrons. Oxygen comes in with 6. There are 2 oxygens, which means 12 electrons. The charge being a -1 means I had to gain 1 electron. We get 6, 18. Nitrogen is going to be our center atom. I want to put my box on my center atom. I forgot to do this with the sulfur one, so I'll double back and do the shape for that in a little bit. I'll go through and now draw my oxygens on the outside. Again, the location of where those oxygens are located doesn't really matter because this is just Lewis structure, not trying to draw the shape accurately. 2, 4, 6, 8. 2, 4, 6, 8. That's 16. NO2, not NO3. So where are we? 16 plus another 2 electrons. Again, I want to place them away from where there's already electrons. I know I have pairs of electrons between atoms. I can turn those into a line. Should now check octets. 2, 4, 6, 8. Both oxygens had the same patterns, so awesome. The oxygens come in as 8 electrons. If I go through and count the nitrogen, 2, 4, 6. Well, dang, the nitrogen actually didn't obtain its octet. So to go through and fix that, what I'm going to have to do is move a pair of electrons from one of the oxygens over to the nitrogen. This is a structure that's going to require resonance, okay? And it's going to need it because I could move electrons from either nitrogen or either oxygen. So the first pair I'm going to move from the right-hand side, but I could have just as easily removed it from the left-hand side. And I'm kind of guessing at where these things are just for the sake of colors. And both of these would be valid options, and I would need to show both if I was going to get correct or full credit for having drawn the Lewis structure. If we now go through and check the nitrogen, we'll check just on the top one, 2, 4, that's a 4, 6, 8 electrons. The nitrogen does have 8 electrons. I didn't touch the other oxygen, so we'll leave that one alone, but the one to the right, I did mess with the electrons, so let's count it. 2, 4, 6, 8. It does still have its octet. So the octets are still satisfied, and I would have my correct structure. Whoops. Saw that I forgot the lone pair on the bottom structure. To get full credit, I do have to acknowledge that it was negatively charged, so I would have to include brackets. These should be done individually. -1, negative. Either one of those options is okay. You don't have to circle it. That's just kind of a reflex from organic chemistry for me. And I'm going to erase that so we can now evaluate shape, which I forgot to do with the sulfur. So we'll go back and look at that one in a little bit. So nitrogen, we decided was our center atom. And again, it doesn't have to be. It's whatever atom we've decided when we're looking at this shape. Okay? That center atom, if we go through and look at the groups of electrons, yes, there's electrons, yes, and yes, which means there are 3 groups of electrons. 3 groups of electrons is going to lead me to the trigonal, because we've got 3, planar, and there's no H in planar, or maybe it's a really silent H, trigonal planar geometry, okay, electron geometry. The next part is acknowledging bonding versus non-bonding. If we go through and look at this, we have 2 bonding groups, and we have 1 non-bonding group. around that nitrogen. Those two pieces of information together lead us to the bent geometry for the nitrite ion, okay, or the bent molecular geometry. Right? And that's how we would go through and assign these things. So memorizing the charts isn't strictly necessary, but if you have them memorized, you're able to jump to these names a little bit quicker and easier, or with a little bit more fluidity that could save you time when it comes to an exam. So having those pieces memorized is a good idea. Okay? I'm going to go ahead and erase all of that and bring back up our SO3 minus 2 because we didn't look at its geometry. So we'll pull that out really quickly. 8, 8, 8, 24, 26, which is what I believe I said we had. We had 6 from sulfur, oxygen at 6. There were 3 of them, and our charge was a minus 2, which means we add 2, 18. Yeah, 26. So just wanted to make sure that we had the right structure. Sulfur is, again, our center atom. So we would go through and look at its electron geometry. All 4 faces have electrons, 4 groups of electrons. This means our electron geometry is going to be tetrahedral. Sorry for the silence. Is going to be our tetrahedral geometry. Right? The next part is to evaluate, are all of those groups bonding, okay, or not? If we go through, we have bond, bond, bond. So we have 3 bonding, and we have 1 non-bonding. If we followed our chart out correctly, what we should notice for that pattern is for our molecular geometry, or molecular shape, that is no longer tetrahedral, that is trigonal. Okay, like we had before, except this time it's not planar. Okay, it's not planar because we're in that tetrahedral category. It's trigonal pyramidal. Okay, forming kind of a pyramid shape. So if you took the tetrahedron but just chopped the top of it off, the other 3 pieces don't move. They're still there. So you still have that kind of trigonal shape. Okay, and we've now got all of those shapes figured out for you. So those were now all solved for you. I would fully expect that if you've watched all the way through this, that you would deserve some kind of inside information that maybe one of those structures would show up on an exam. And I would bet that that's probably true. This next exam is probably going to have one of those written out for you. Okay. So thank you for listening all the way through. It is much appreciated. And with that, we are done with Unit 1, like the entire thing. I don't think I have any more to give you.